So good morning, everyone. I hope that you're all doing well since the last time that we met. So today we are going to look at how do we move from energy statistics to energy balances. And we will also go even further and see how we can use energy balances to calculate CO2 emissions from fuel combustion. So I will be joined later by Taylor and by Puya, who will help with who work on the balances and on calculating CO2 emissions. So very briefly, this is the agenda. So today we are at the statistics free session, and then next on Thursday, we will look at the statistics 4 on prices and energy efficiency. So again, very quickly, some housekeeping rules. So if everything is virtual, we recommend that microphones are turned off. If you have questions, use the question and answer box or raise your hand and we will allow you to take the floor. And if you have any further questions, you can send emails to me, to Darlene, or to the Africa program. So this is the agenda for this session. So as you know, the energy balance, it's a natural starting point to study the evolution of the domestic energy market, forecast energy demand, and also to monitor impacts of energy policies and to assess potential areas for action. So today, this presentation will be divided into 5 parts. We will see what is an energy balance, how it differs from the commodity balance, and how the IEA energy balance is constructed. We will then see the importance of calculating an energy balance and also the advantages you can derive from it, such as generating indicators for analysis and CO2 estimations. We will also study the principles of creating an energy balance. We will look at the IEA methodology and definitions used with also a focus on calorific values. I will show you also how an energy balance looks like and how the transformation of energy happens in the energy balance. And finally, we will see how with the data from the energy balance, we can calculate the CO2 emissions from fuel combustion. So let's get started. So the energy balance, it's a presentation of the basic supply and demand data for all fuels in a manner which shows the main fuels together, but separately distinguished and expressed in a common energy unit. So the energy balance, it takes the form of a matrix where the column represents the different energy sources, which are products, and which are the products categories, and the rows, they represent all the different flows grouped into 3 main blocks. You have the energy supply, the transformation, energy use, and the final consumption block. So to develop an energy balance from the set of commodity balances, there are 2 main steps. First, all the data are converted to a common energy unit, which allows us to compute the total column. And then you have to do some reformatting in order to avoid double counting when summing all the products together. So this format, it allows the easy comparison contribution that each fuel makes to the economy and their interrelationship through the conversion of one fuel into another. Another way to present an energy balance, it's through the Sankey Flow, which is a graphic format. This is exactly the reverse matrix of the table that we have shown before with the products and flows. It gives you a quick visual picture of the energy sector of the country over time. The arrows here, it shows the energy flows from production on your left to final consumption on your right. You can see that flows can be combined together, they can be splitted and traced through a series of events. And the width of the arrows, they are proportional to the flow quantity. if you go on the IEA website, you have the link here below on the slide. You can really see how over time as well the energy balance has evolved. You can use the timeline to see from 1971 to today how the energy consumption of different fuels and sectors have evolved. This is the Kenya Sankey Flow from the IEA website. So here very quickly you can see what are the main fuels that contribute to the economy. You can see that there's some oil products imports, there's a bit of coal imports, you can see some biofuels and waste production, and you can see also there's geothermal production, which is quite big in Kenya. And this is one of the specificity of Kenya in Africa. You can also see how these products, for example, the oil imports, some of it is used, a little bit is used for power stations, and the rest is used in the final consumption sector. Most of it goes to transport, but some of it goes to industry as well. You have some coal imports, and all the coal is used in the industry sector. And then you have biofuels, so solid biomass mainly, that is used mostly in the other sector, which here refers to the residential sector. And then you have geothermal that's used to produce electricity, and a bit of hydro as well, which is the light blue line. So instead of looking at numbers, visually you can see how your country differs with other countries and what's happening, how it's evolving. So now let's do some Menti questions on energy balance. I will share the Menti now. Yeah, so the first question, so please first connect to www.menti.com and use the code that appears up on the screen, 17, 45, 37, and 63. So this is the code. I'll just copy the code and put it in the chat box here. Sorry. So please connect to www.menti.com and use the code that appears on the screen, 17, 45, 37, and 63. So some of you are replying yes, and one replied no. So is it possible to have a statistical difference which is equal to 0 in a statistics table and not 0 in the related energy balance? So for example, you have a specific fuel, I don't know, you have oil that is produced or imported, and so you have a certain amount for your domestic market, and then you have consumption, and so everything matches. So you have 0 statistical difference in, for example, for coal in kiloton, but then when you create your energy balance in terajoules, in ton of oil equivalent, whatever energy unit, you end up with a statistical difference there. So is this possible? So very good. Let's look at the right answer. So indeed, this is possible because of, you will see in the presentation where I will explain this in more details, but sometimes if you're not using the good calorific values for the different products and flows, you can end up with calorific, with a statistical difference in energy terms that did not exist in physical terms. So next question. In an energy balance, you see a positive number in the total column of a transformation flow. Is this possible? So here we are saying that, in the energy balance, you have some sign conventions in the transformation sector. So you have positive numbers, negative numbers. So what does this mean? And in the total column, you can end up with the total, it's the sum of the products in the same unit. So here, is it possible that you end up with a positive number here? So let's take again an example so that you better understand. For example, you have your refinery. That uses crude oil as an input. So the crude oil will appear as a negative number. And then you have oil products, which is the output, that will be a positive number. And then the total column, it's the sum of this transformation process. So your input and your output, and there, can you have a positive number? Usually, so here we give three possible answers. Is it yes? It means that the transformation efficiency is very high. Is it no? Transformation outputs are always equal to the inputs and totals are always equal. Or no, totals are always negative because the transformation efficiency are always lower than 100%. So maybe take the example, you have 100 of crude oil input. Can you have 110 of oil products output? And then in your transformation total, you have 10 because you have minus 100 plus 110. Can you have a positive? Is it normal to have a positive number then in the total? Or is it more normal to have 100 of input and 95 of oil products, and then your total will be -5? So I think I kind of gave you the answer in my explanations. So let's look at the right answer here. So here, no, it's not that it's not possible. It means that there's a problem. So totals should always be negative in energy terms because efficiencies are always lower than 100%. Because as I gave you the example of the refinery, if you're putting 100 terajoule in a refinery of crude oil, then you cannot get more than your input in energy terms. So your total should normally be negative. So this was on Menti. Now let's move to the presentation itself. Let me wait, just give me 1 second. I think I have too many things open. So if I stop sharing, okay. Now, let us see in more details the importance of calculating an energy balance and what you can derive from it, such as generating indicators for analysis and CO2 estimations. The energy balance is a way of reporting energy data in a common unit and with products aggregated by category. It has many benefits and uses. By presenting all the data in a common energy unit, the energy balance allows users to see the total amount of energy used and the relative contribution of each different source for the whole economy and for each individual consumption. It also allows comparison of the shares of each source in the energy supply of a country and in each sector of economic activity. Different countries can be compared when they are calculated with the same methodology. With an energy balance, you can develop various aggregated indicators, such as consumption per capita or per unit of GDP, and to estimate CO2 emissions from fuel combustion. A country can determine its dependence on energy imports or exports. With an energy balance, it is possible to analyze energy efficiency. The statistician also uses the energy balance as a high-level check on the data accuracy, as large statistical differences in energy units, apparent energy gains, or large losses in transformation processes may all indicate underlying data problems. Also, it allows us to have a good basis for making forecasts and projections to achieve climate goals and to check that policies in place are well implemented. If you want to exploit the full potential of an energy balance, it is recommended to combine energy statistics with economic indicators. These new aggregated indicators allow us to understand how energy impacts society and economy. For example, we can calculate the energy intensity and self-sufficiency of a country. Energy intensity is a measure that is often used to assess the energy efficiency of a particular economy. The numerical value is traditionally calculated by taking the ratio of energy supply to gross domestic product, indicating how well the economy converts energy into monetary output. The figure on the left side shows us how primary energy use and GDP have changed globally over time relative to a normalized year of 1990. As you can see, GDP and total energy supply are decoupling, and this can be due to several reasons such as structural changes and efficiency improvement. In sub-Saharan Africa, the energy intensity is decoupling less quickly than globally. Obviously, low energy intensity is the desired goal because it represents an efficient allocation of energy resources to generate wealth and a high quality of life. So it is logical to expect energy intensity to increase and for GDP and energy use to be closely coupled during the initial stages of development of a nation,
Since the early years of access to electricity and utilization of more abundant energy includes many energy-intensive activities. The developing economies will need to produce a tremendous amount of cement for roads and buildings, as well as steel for automobiles, appliances, and telecommunication infrastructures. These will be new users, some of which will naturally be energy intensive. We can also compare countries to see where each other stands for. In this graph on the right side, you can see that OECD countries are less energy intensive compared to non-OECD countries for the reasons I mentioned before. In sub-Saharan Africa, the differences between countries are quite large. Some countries, such as Democratic Republic of Congo, is more energy intensive compared to Ghana. Another indicator is self-sufficiency. The energy self-sufficiency rate is the ratio between national primary energy output and consumption of primary energy in a given year. This rate may be calculated for each energy types or overall for all types of energy. A rate of over 100% indicates a national production surplus in relation to domestic demand and therefore net exports. For Africa, if you remove biofuels from the energy mix, then the self-sufficiency declines a lot. In sub-Saharan Africa, a very high self-sufficiency rate is due to the top oil producers. Now, if we compare the self-sufficiency by country, we see that again there are differences because of biofuels and waste. For example, for Uganda, the self-sufficiency can seem very high at around 90%. But if we look at the energy balances, we see that there is a very high share of traditional biomass in the energy mix. And if not accounted, we see self-sufficiency drastically decreasing to 16%. Conversely, for Nigeria, who is a strong oil producer, self-sufficiency even increased because most of the oil is exported and biofuels consumed domestically. However, concerns for oil producers in Africa are on the midstream infrastructures, namely refinery, and countries will indeed import most of the finished products beside a large national oil production. In the case of Ethiopia, if we remove biofuels from the self-sufficiency, then Ethiopia is producing only 20% of its energy demand. Another indicator is the residential consumption per capita. So how much are we consuming at home? In this chart, we can see that the difference between OECD countries and sub-Saharan Africa is quite large. In sub-Saharan Africa, we consume 50% less energy in residential sector compared to OECD countries. However, traditional biofuels used in sub-Saharan Africa is quite large and inefficient, and the useful energy consumed per capita is much lower. This is how the picture looks like if we exclude solid biofuel consumption, which is very inefficient consumption per capita in sub-Saharan Africa. We see that the gap with the OECD is even higher and consumption per capita is very low. Now, let us look at the methodological assumption underlying energy balances. As you know, energy data are generally collected independently across different commodities. To develop an energy balance from the set of commodity balances, there are two main steps. The first one is to convert the natural units in the different commodity balances, that is for coal, oil, gas, renewables, and electricity, to the chosen energy unit. Here it is kiloton of oil equivalent in the IEA balances, but many countries use terajoules. By multiplying by the appropriate conversion equivalent for each natural units, which are calorific values. The second step is some format changes. We need to do some reformatting in order to avoid double counting when summing all products. We need to rearrange the converted commodity balances along one another, rearrange certain of the rows, and introduce a sign convention in the transformation sector. What is a calorific value? It is the amount of heat obtained from one unit of the fuel, and it is the only way to convert a fuel quantity from natural units, that is mass or volume, into energy units, that is KTOE. It is very important to collect good quality calorific values in addition to good data in physical units. As you can see, in this commodity balance, there is no statistical difference. But when we convert to the energy balances using calorific values, then a statistical difference appears. Why? If we look carefully at the calorific values in the middle table, you will notice that the calorific value for the input to electricity and consumption is different from the production and imports. This is something to query with the country. So as you can see, calorific values can be a good check for data quality control. Now, let us look into more details at the principles of an energy balance. The main methodological choices underlying energy balances that can differentiate the final balances layout across organizations are as follows. The IEA energy balance methodology is based on a common unit of account and on the calorific content of the energy commodities. The IEA balances are expressed in terms of net calorific value. The change from the original units to tons of oil equivalent implies choosing coefficients of equivalence between different forms and sources of energy. When constructing an energy balance, it is necessary to adopt conventions for primary energy from several sources, such as nuclear, geothermal, solar, hydro, wind, etc. For each of these sources, there is a need to define the form of primary energy to be considered. There are essentially two methods that can be used to calculate the primary energy equivalent of these sources: the physical energy content method or the partial substitution method. Also, temperature adjustments made by countries should also be taken into account. And finally, we have to know if the balance is based on a fiscal or a calendar year basis. First, we have to choose an energy unit. Then we have to choose the energy unit. It can be any energy unit. It can be British thermal units, ton of oil equivalents, joules, watt hours. The unit of account adopted by the IEA is the ton of oil equivalent, which is defined as 41.868 gigajoules. This quantity of energy is within a few percent equal to the net heat content of 1 ton of crude oil. The conversion of the IEA energy balance to any other energy units would be straightforward. The choice of the ton of oil equivalent is based on the history of the IEA creation after the first oil crisis. The difference between the net and the gross calorific value for each fuel is the latent heat of vaporization of the water produced during combustion of the fuel. This heat is lost and cannot be recovered. For coal and oil, the NCV is about 5% less than the gross. For most forms of natural gas and manufactured gases, the difference is approximately 10%, while for electricity and heat, there is no difference as they are not combusted. The use of net calorific values is consistent with the practice of the statistical offices of the European Communities and the United Nations, and most importantly, it represents the useful energy. Generally, the IEA adopts country-specific, time-varying, and for some products, flow-dependent net calorific values supplied by national administrations for most products. For coal, the IEA has adopted specific factors supplied by the national administrations for the main categories of each quality of coal and for each flow or use. For natural gas and crude oil, specific factors have been used for production, imports, exports, and electricity generation based on consultations with experts from the national administrations. In the case of oil products, the IEA applies regional calorific values. So now we know how to convert combustible fuels in energy units, but what about nuclear, hydro, and other renewables? Why is it so important to compute this input, the primary energy equivalent? Because it is important to quantify the primary energy supply in order to calculate the total energy supply. A very important methodological choice is the definition of the primary energy equivalent for the electricity and heat produced from non-combustible sources such as nuclear, geothermal, solar, hydro, and wind. The information collected is generally the amount of heat and electricity produced, represented in the balance as an output of the transformation. Conventions are needed to compute the most appropriate corresponding primary energy input to the transformation, both in forms and in amount. For each of the following sources, that is nuclear, geothermal, solar, hydro, wind, tidal wave ocean, and solar PV, there is a need to define the form of primary energy to be considered. For instance, in the case of hydro energy, a choice must be made between the kinetic energy of falling water in the turbines and the electricity produced. For nuclear energy, the choice is between the energy content of the nuclear fuel, the heat generated in the reactors, and the electricity produced in the nuclear reactor. For solar photovoltaic electricity, the choice is between the solar radiation received and the electricity produced. The principle adopted by the IEA is that the primary energy equivalent form should be the first energy form downstream in the production process for which multiple energy uses are practical. The application of this principle leads to the choice of the following primary energy forms: heat for nuclear, geothermal, and solar thermal, and electricity for hydro, wind, tidal wave ocean, and solar photovoltaic. We have now identified the form of the energy input, but now we need to quantify it. There are essentially two methods that can be used to calculate the primary energy equivalent of these energy sources. The partial substitution method, which at the IEA we do not use anymore, and the physical energy content method. The physical energy content method uses the physical energy content of the primary energy source as the primary energy equivalent. As a consequence, there is an obvious link between the principles adopted in defining the primary energy forms of energy sources and the primary energy equivalent of these sources. For instance, in the case of nuclear electricity production, as heat is the primary energy form selected by the IEA, the primary energy equivalent is the quantity of heat generated in the reactors. In the absence of country-specific information, the IEA estimates the primary energy equivalent from the electricity generated by assuming an efficiency of 33%. This is derived as the average efficiency of nuclear power plants across Europe. For geothermal electricity, the primary energy equivalent is the quantity of heat, and a similar back calculation is used when the quantities of steam supplied to the plant are not measured. So assuming a thermal efficiency of 10%. This figure is only approximate and reflects the fact that the steam from geothermal sources is generally of low quality. If data for the steam input to geothermal power plants are available, then they are used directly as primary energy equivalent. Similarly, for solar thermal plants, the heat supply is back calculated assuming a 33% efficiency of conversion of heat into electricity, reflecting relatively low working temperatures, although central receiver systems can reach higher temperatures and therefore higher efficiencies. In the case of hydro, wind, and solar PV, as electricity is the primary energy form selected, the primary energy equivalent is the physical energy content of the electricity generated in the plant, which amounts to assuming an efficiency of 100%. So when the primary energy form is heat, we have losses. Let us see a few examples to illustrate this concept. For wind, as we have an implied efficiency of 100%, so with 1000 TOE of electricity produced, the primary energy equivalent is 1000 TOE of wind. In the case of nuclear, as the implied efficiency is 33%, so for 1000 TOE of electricity produced from nuclear, the primary energy equivalent is around 3000 TOE of nuclear. In the case of geothermal electricity, as the efficiency is 10%, so for 1000 TOE of electricity produced from geothermal, we need 10,000 TOE of geothermal. For geothermal heat, the efficiency is 50%. So for 1000 TOE of heat produced, we need 2000 TOE of geothermal. Now, let us look again at the energy balance in tabular format and how to read it. These are the key elements to understand in an energy balance. We have three distinct blocks. The top part, which is the energy supply block, the middle part, which is the transformation and energy use part, and the last block, which is the final consumption. The last two blocks are what we refer to as demand. Only production of primary products are shown in the production row in order to avoid double counting. Secondary products are shown in the transformation block. That is why for oil products and electricity, the production cell is 0. The total energy supply row allows users to see the total amount of energy used and the relative contribution of each different source. Do you think this country is producing oil products? In the transformation block, there is a sign convention. Negative values represent an input and positive values represent an output. Transformation losses appear in the total column as negative values. In the total final consumption block, you have all the different sectors consuming fuels such as industry, transport, residential, and non-energy use. In this table shown in this slide, the energy balance is cut. That is why in the total final consumption, you are seeing only industry, but the table continues. As all fuels are reported in the same unit, then we are able to compute the total products column. In the transformation sector, the negative value in the total cell represents losses of the transformation process. I hope that this presentation has helped you understand some of the dynamism of the energy balances. Here are some key takeaways from the balances. Good energy balances are a compact source of energy information and is very convenient to use. However, a good energy balance requires good quality statistics, and not only in terms of data, but also calorific values. It also enables statisticians to run accurate checks of energy statistics, such as efficiencies, losses, etc. Also, they are the foundation for basic energy indicators, energy account, CO2 emissions estimates, and for modeling.
This chart represents the global CO2 emissions from fuel combustion. The share of the OECD countries in global emissions.
I think we will just pause here. I'm sorry. We will just pause here for some questions on balances. So if you have any questions regarding the presentation that you just watched, please send us your questions in the Q&A box. I've been joined by my colleague Taylor Morrison. So please let us know if you have any questions. Or you can also raise your hand. So does it mean that the presentation was very clear? You understood everything? You can now move easily from energy statistics to energy balances. You understood everything on how to make the conversion. So maybe a question on my side. How many of you have ever worked on energy balances? Do you have experience on building energy balances? So I would be interested in hearing from your experience on this. There's a question on what's the conversion of 1 megawatt to TOE. So for the conversion from one energy unit to another, you can find it on internet. It's a direct conversion. Maybe Taylor, if you can share this conversion.
Sure. Just one note is that megawatts is actually power.
Yeah.
So you need that's TOE and megawatt hours are both energy units and comparable.
Yeah, exactly. So usually we convert TOE to megawatt hour or megawatt hour to TOE. There's one question from the energy balance presentation. Does it mean that energy balance is surmounted at a point of time for every year, or can it be computed for period of time? So, I mean, yes, you can create energy balances if you want for weekly data but at the IEA, we collect it for annual. But if there is a need on your side, and if you have the information at a more disaggregated level, then definitely you can create your energy balance for a shorter period of time. But that's the most common, it's the annual energy balances. Would you like to add something on this, Taylor?
No, it's really up to the user as long as it's explicit, I think.
Yeah. So how do you obtain the consumption data by sectors? Would you like to take this one, Taylor? I think here, I mean, the data we collect, we get it from the data providers when the information is available at the national level. And it happens that when we don't receive this information, we estimate it. But Taylor can maybe give more information.
Sure. So as Zakia said, if we're lucky, the statistics office of the country we're working on will have that information through different surveys and their own estimates. And they can do this by collecting residential surveys, surveys from manufacturers and other industry sectors. But it's often the case that this data is not available. So in that case, we may have this data, for example, just 1 year and not on an annual basis. So in that case, we would use that division of consumption by sector and apply it to future years, which is just a rough estimation. It may be the case that we don't have energy data, but we do have GDP by sector or some type of economic indicator by sector. So we can apply that to approximately estimate energy consumption by sector. And then also we may, if we don't have any data at all, we know from looking at other countries what type of consumption to expect by fuel, and we can estimate it that way. So for instance, gasoline we know is mostly consumed in transport sector and road. So if we don't have any information, then we would have to simply allocate it to road.
Yeah. Any other question on the energy balances? I think if we don't have any other question, then we will move on with the next step of using energy balances to calculate CO2 emissions. Thanks a lot, Taylor, for joining for the Q&A session.
Thank you.
Okay. So can you connect again to www.menti.com and use the code that appears up on the screen, 1745 37 and 63. I try to put it in the chat box. It's the same as before. It's the same code as earlier. So 1745 37 63. So we'll just have one question on CO2 emissions. So the question is, if you have your energy balance calculated with a reasonable level of granularity, can you estimate your country's CO2 emissions from fuel combustion? So here, if you have your energy balance calculated with a reasonable level of granularity, can you estimate your country's CO2 emission from fuel combustion? I'll give you some time to reply. So you have three possible answers. Is it yes, you can calculate by multiplying your total energy consumption by a fixed factor provided by IPCC? Or no, you cannot because you need more information beyond energy balances. Or yes, you can use the standard IPCC carbon intensity for each fossil fuel burned in the country. So let's look at the right answer now. So the right answer is indeed yes, with an energy balance that has a good level of granularity. So you have your energy balance by fuel, then you can use the standard IPCC carbon intensity for each fossil fuel burned in the country to calculate your emissions, your CO2 emissions. So now let's continue the presentation.
This chart represents the global CO2 emissions from fuel combustion. The share of the OECD countries in global emissions has decreased from over 55% to around 35% in less than 20 years. However, the global emissions have increased at a pace of around 2% per year, mostly driven by the emission growth in the non-OECD countries. The small blue line on top represents the sub-Saharan Africa emissions, excluding South Africa, and the orange line represents the other African countries. Despite a strong increase in the past 20 years, they correspond to only 4% of the global CO2 emissions, while representing about 15% of the global population. Credible and validated energy data are pivotal in providing high-quality emission estimations and greater confidence in the policy analysis. Access to comprehensive data enables detailed analysis of key sectors, fuels, and driving factors of emissions, both on a country-specific and global levels. This figure represents the sectoral share of CO2 emissions in the OECD, non-OECD, Africa, as well as a few African countries. The electricity and heat generation correspond to about 2/3 of global energy-related CO2 emissions from fuel combustion. Disaggregated data allows allocating the emissions associated with power generation to the end sectors and provide a more complete understanding of real drivers of CO2 emissions. The graph on the right represents the sectoral emissions after reallocation of power generation emissions to the end sectors. As you can see, in the OECD countries, buildings, transport, and industry are together responsible for about 85% of total emissions, while among the non-OECD, industry alone represents more than 50% of the total share. In the sub-Saharan Africa, however, transport remains the highest source of emissions, representing 50% of the total. Detailed emissions data enables populating matrix, which can be used to discuss the macroeconomic driving forces behind CO2 emissions and provide insightful input for effective energy and climate policymaking. The formula on the top is known as the Kaya identity, which allows decomposition of the total CO2 emissions into 4 macroeconomic factors: population, GDP per capita, total energy supply per GDP, and CO2 emissions per unit of total energy supply. As illustrated in the graph on left, among the OECD, decreasing the energy intensity of the economy alongside lower carbon intensity of the energy mix have been driving the emissions down. On the other hand, among the non-OECD countries, increase in population, GDP per capita, and carbon intensity of the energy mix have been driving upwards trends in CO2 emissions, while the reduced energy intensity is slightly offsetting this increase. In Africa, the increase in population and wealth are the main drivers of emissions increase. Most of you are perhaps already familiar with the concept of greenhouse effect. CO2 alongside methane, N2O, water vapor, fluorinated gases, and ozone are known as greenhouse gases. The greenhouse effect refers to the circumstances where the short wavelengths of radiation from the sun pass through these gas molecules, but the longer wavelengths of the re-radiation from the Earth's surface are unable to pass through them. The trapping of the long wavelength radiation leads to more heating and a higher resulting global mean surface temperature. CO2 is the major contributor to global warming, and combustion of fossil fuels is the main source of global anthropogenic CO2 emissions. The burning of fossil fuels affects the concentration of CO2 in the atmosphere. Before the Industrial Revolution, the amount of CO2 in the atmosphere was about 288 ppm. We have now reached about 414 ppm, and we are on the way to doubling the amount of CO2 in the atmosphere by the end of this century. There's currently a strong scientific consensus globally regarding the role of emissions caused by the anthropogenic activities in increasing of global mean temperature. According to the IPCC special report of 1.5 degrees C, global temperature increases by the end of the century is likely to reach up to 5 degrees C above the pre-industrial levels if the current policy trends are continued and no significant action is taken. The United Nations Framework Convention on Climate Change, UNFCCC, is an international treaty adopted in 1992 to address climate change. Starting 1995, the parties to the convention have met annually to assess progress in dealing with climate change. In year 1997, the Kyoto Protocol was adopted and established legally binding obligations for the developed countries to reduce their greenhouse gas emissions. At the 21st Conference of the Parties, or COP21, in Paris, countries approved a new global climate change agreement, the famous Paris Agreement. The aim is to limit the global average temperature increase to well below 2 degrees C, with efforts to limit this further to 1.5 degrees C. The Paris Agreement was adopted in 2015 and came into force in 2016, with 187 countries ratifying it. In COP26, which is planned to be held in November, this year, countries are expected to communicate or update their national climate targets. The IPCC, with the help of IEA, has developed and refined an internationally agreed methodology for the calculation and reporting of national greenhouse gas emissions. The guidelines is called the 2006 IPCC Guidelines for National Greenhouse Gas Inventories Reporting, which is caused and used by the countries to report their emissions to UNFCCC. The IEA estimates of CO2 emissions are based on this credible international methodology. It's important to note that according to the IPCC guidelines, countries report their emissions under 5 different categories, as listed on the page. IEA deals with category 1, which corresponds to energy-related emissions only. Moreover, the energy-related emissions are divided in 3 subcategories under the guidelines. And the IEA estimates cover category 1A, which corresponds to the CO2 emissions resulting from fuel combustion of fuels only. However, as shown by the graph, energy is at the core of the greenhouse gas estimation, and the CO2 emissions from fuel combustion, which are covered by the IEA analysis, correspond to around 3/4 of total global greenhouse gas emissions. IEA CO2 estimates are based on globally recognized guidelines throughout the process. Our data collection process starts at the country level from national statistical or energy offices, where we collect energy data in physical units in the form of IEA energy statistics, which you are by now familiar with. From there, and based on the international recommendations for energy statistics as published by UNSD, and with the help of the net calorific values for various fuels, this information is put together in energy terms and forms the IEA energy balances, as it was discussed in detail earlier today by my colleague. Finally, and with the help of the default emission factors and methodology provided by the IPCC guidelines, IEA CO2 emissions are estimated. It's important to note that the IEA estimates of CO2 emissions from fuel combustion are a global database obtained following harmonized definitions and comparable methodologies across countries. However, they do not represent an official source for national greenhouse gas inventory submissions to UNFCCC. The IEA uses the simplest, the Tier 1 methodology to estimate CO2 emissions from fuel combustions based on the IPCC 2006 guidelines. Based on the Tier 1 method, the CO2 emissions from fuel combustion for a given fuel are calculated by multiplying the amount of fuel consumed in energy terms by the default fuel-specific emission factors provided in the IPCC guidelines. The computation follows the concept of conservation of carbon, which assumes that all carbon contained by the fuel burnt is oxidized and emits CO2. Emissions are then summed across all fuels and all sectors to obtain the national totals. It is also important to note that various fuels have different emission factors. For example, as you can see on the graph, combustion of a unit of a carbon-intense fuel such as a blast furnace gas corresponds to around 5 times of CO2 emissions comparing to when the same amount of natural gas is combusted. And now to conclude, there's a scientific consensus regarding the role of anthropogenic CO2 emissions in increasing the greenhouse gas concentration in the atmosphere and the global warming. Effective emissions mitigation requires collaboration on a global level, and up-to-date and accurate information on greenhouse gas emissions are essential for effective climate policy making. And most importantly, the greenhouse gas emission estimates are only as good as the energy statistics which underlies them.
So this is the end of the presentation on the CO2 emissions, and I'm joined by my colleague Puya, who is an expert on emissions, and so if you have any questions, please don't hesitate. Hi, Puya.
Hello, Zakia. Hi, everyone. I'm happy if there's any questions.
So you have seen how you can use energy balances information to calculate CO2 emissions. Are there any colleagues in the participants who make this calculation, who works on emissions calculation here? If you would like also to share your experience, don't hesitate.
Yes, it would be interesting to know if is anyone within you also involved with the submissions to UNFCCC. As we know, there's not always the best synergy between the energy and climate reporting organizations. So one of the areas that we've been working a lot is try to align this data as much as possible.
Yeah. No question? So today people are a bit shy compared to previous sessions where we used to get more queries. Oh, we have two questions. So the first one is, how accurate is the CO2 calculation?
So essentially, the most important thing, how accurate the CO2 estimation would be, lies within the accuracy of the energy data underneath it. That's, I would say, the most important. So that's why we need to ensure and try as much as possible that the underlying energy data, which we base the estimates are as accurate as possible.
Yeah.
From there, as you saw, we use the Tier 1 method within the IPCC methodology for estimating the emissions, which essentially there are default emission factors, few specific ones which are applied to the activity data to estimate the emissions. And in terms of CO2 emissions, since the conservation of carbon principle is true, and essentially when you burn a fuel, almost close to 100% of its carbon content is oxidized, then the default factors provide an actual very accurate estimation. However, when we want to estimate non-CO2 emissions, for example, methane or N2O, which can also result from combustion of fuels, then in that estimation, the accuracy of the factor is more dependent on the type of the technology and facility and all that. But in terms of estimating CO2 emissions, essentially the most important thing is the underlying energy data.
Exactly. Whatever is your input, the quality of your output depends on your input. So good basic data that fits the energy balances is important. And we have a few questions. So the next one is, does heat emissions from electricity generation have an effect in global heat, or is it insignificant?
Heat emissions from electricity generation?
Yeah.
Not sure if I understand the question, but
maybe it means heat production.
Yeah, generally, I mean, the category of emissions that we looked at was category 1A, which corresponds to fuel combustion emissions. So whenever we are combusting any fuel in order to produce energy, the resulting emissions is accounted for under this category that we just followed. So similarly, when we are combusting fuel for power generation, which includes electricity and heat generation, the emissions are included within these estimations, correct?
Yeah, thanks, thanks, Puya. Then we have another question. How do you convert CO2 emissions to number of trees saved and planted?
Well, that is that's not our expertise to do that, but essentially experts on national resources and forestry conservation, the way they do it is that they have estimates for various types of trees, how much CO2 is being conserved by that specific tree type. And then with that, you can have an estimation of for preventing this amount of emissions per year, what amount and over what period of time of a specific tree can be planted.
Yeah.
All these emissions corresponding to natural carbon sink falls within category 3 of the IPCC estimations, which is called agriculture, forestry, and land use. So any emissions and also sinks, natural sinks, carbon stock change within organic dead matter, biomass, harvested wood products, and all that falls within that category.
Okay, thank you. There's another question. In the presentation, it was indicated that the IEA CO2 emissions do not represent national submissions of greenhouse gas inventories to UNFCCC. What could be the variances? There's a software from UNFCCC on GHG computation. Is the IEA computation aligned to this?
Yeah, so that's a very important, good question. So as you correctly mentioned, the IEA estimates provide a harmonized, comparable estimates across the countries for CO2 emissions, but they're not the official national source of submissions to UNFCCC. That is, as you are aware, done by the countries themselves. The methodologies followed by us and UNFCCC are almost aligned, not 100%. There is, to give you some technical details, there are some few categories of fuel combustions which lie within the IPPU or industrial processes and products used while reported to UNFCCC. However, in our estimates, we include all the emissions associated with fuel combustion in our reporting. So that's a slight difference that we have with the data submitted to UNFCCC. But again, the main differences between our data and what is submitted to UNFCCC comes from the underlying energy sources. So that is why we've been working with countries across the member countries as well as other countries to try to maintain and make sure that there's alignment within the energy data submitted to IEA, as well as the ones used to estimate the emissions submitted to UNFCCC. As much as there's more alignment within that energy data, then our estimates are actually more aligned with the ones submitted to UNFCCC. I also want to make sure that as one of the stages and steps of the official review process, which UNFCCC does to the national submissions, the underlying energy data within the greenhouse gas inventories is benchmarked against our energy balances, which we essentially use to estimate our emissions. So our data essentially is used as part of the steps to verify the accuracy of the submissions to UNFCCC. And yeah, those are the main differences. And the methodology, as I explained, is pretty much the same with very slight differences.
Thanks a lot, Priya. Next question. How is energy efficiency, say for vehicles and machines, taken into account given that the IPCC is predetermined?
So in terms of energy efficiency, that would result, if there are any efficiency measures in place, that just results in less energy consumption.
Yeah.
And when we have less energy consumption, that translates to less emissions when we do the emission estimates. That's how we show it, and we see it in terms of reducing emission. It just corresponds to less energy consumption, and as a result, less emissions.
Thank you. Another question. I'm not sure I saw CO2 emissions computation from electricity from the slides. Can one use grid emissions factors for this computation?
Yes, so in order to estimate emissions corresponding to electricity consumption, typically, for example, when companies have to do now, majority of the companies have to do reporting under the greenhouse gas protocol. So what needs to be done is that they need the electricity emission factor from the national grid that they're using. So for example, if it's a company within France, they would need the grid electricity factor from France. And then based on that and the activity data they have, so the amount of consumption per kilowatt hour they have, and multiplying that by the grid electricity factor, they can estimate the emissions associated with their electricity consumption within a specific year. And obviously, when we have a country which has a more decarbonized electricity mix, like France, which is highly nuclear, then that carbon factor is lower, and the same amount of electricity consumption might result in a lower total emissions comparing to a country which you have a more fossil heavy electricity grid.
Thank you. Very interesting. So that's great. I think we had quite a nice bunch of questions. If you have any more questions, don't hesitate. We have some time today so we can take this opportunity that we also have Puya with us, who knows everything on emissions, to answer your questions. Or if you want to raise your hand and share some of your experience or questions live, don't hesitate as well. I can give you the floor to speak. No more questions? Okay, we have someone who raised, we have Derek Onyoni who raised his hand. So would you like to take the floor?
Yes.
Hello.
Actually, from the response in the last question, I'm trying to follow it up. Is it Puyo said that emissions are relatively related to the electricity, or like the energy consumption? Can we then say that the more the emissions, more the development, because the energy consumption is relative to development now? Because can we say then the more you emit, the more you develop, or the less you emit and then the less you develop because of the energy consumption?
Yeah, so because there was a small issue with your voice, so I'm just gonna try to make sure that I understood what the question is. So the question is that if we want to have development, then that requires energy consumption, and if we consume more energy, that corresponds to more emissions, then how should we proceed? Is that the question?
Yeah, actually, that is the question.
Okay. So yes, obviously, it's not just for electricity. Across the economy, development traditionally comes with energy consumption. especially as the countries are moving to a more industrialized, urbanized society that corresponds to a lot of heavy energy consumption. Imagine infrastructure buildings, road consumption, like electrification and all that. That comes with traditionally energy consumption, which since even right now, a majority of the energy mix comes from fossil fuels, that corresponds to emissions. As a result, yes, development generally comes with more emissions. So what needs to be done, and it's obviously not an easy solution for it, and it needs to be across the sector with all the global players put as much as effort as possible, is to try to decouple development from emissions as much as possible. In order to do that, first of all, is that in order to be able to achieve the amount of development with less energy consumption, so make processes more energy efficient, implement energy efficiency measures across the industry, across various sectors as much as possible, and at the same time try to decarbonize the energy sources as much as possible. So again, you reduce the energy consumption as much as possible by implementing energy efficiency measures, and at the same time try to decarbonize the energy mix by using renewable sources, as well as other low carbon energy carriers across the sectors as much as possible, to essentially be able to have the same economic output with less emissions. So we need to try to, as much as possible, decouple development from emissions, but as you also correctly mentioned, it's not an easy task to do. I hope that answered your question to some extent.
Any other question or comments? We have David also that raised his hand.
All right, thank you. Can you hear me?
Yes, we can.
Yeah, in addition to that question, my question is, in as much as you want to relate development with the increased emissions, what about now when you're moving towards like what's happening in globally, the issue of transition to green energy, whereby you find the more green energy you have in terms of consumption, in terms of your energy mix, the emissions are less. Would that be one of the solutions? Because you cannot stay without developing. So that you say that as you are developing, then can we increase the transition towards green energies? But as you move towards conventional from non-green, if I may call it that, to green energy, then you also take into consideration things of stability in the grid and other things. Of course, I know there's the aspect of in Africa, you have a lot of petroleum product being used, especially in the transport sector. But we've seen the incoming of electric cars and all those other developments which are likely to come later. So it says in the future, are you saying that it's still more as development increases, you still have more emission, or is that scenario likely to change as you transition to green energies? Thank you.
Yeah, David, thank you for question and your thoughts. Again, yes, as you mentioned, it's very important to try to plan future development as much as possible in a way which allows us to decouple that from increased emissions. So as one important thing is that typically when you have investments for energy infrastructure, they have a large lifespan. So for example, if someone builds a power plant right now, you typically will have that in operation for the next 30, 40 years. And this highlights the importance of making the right decisions right now and try to essentially have that, as you mentioned, more reliance on low carbon green technologies as much as possible in the planning right now to be able to decouple the corresponding development from the emissions. As you mentioned, there are many challenges, including managing the frequency on the grid, which comes with dispatchable renewables. So you always need to take into account with various technologies. There are transformers now that help that. There is demand response, which essentially allows technologies which allow you to manage your electricity demand depending on the availability on the grid during the different times of the day to help. The EV cars, as you mentioned, they can also, despite the fact that they're obviously increasing the demand for electricity, but they can also help providing some electricity to the grid at some point. So for example, when the demand is high on the grid, you can have your EVs plugged in and electricity going backwards into the grid to essentially help with the stabilizing that. So there are various technologies. A lot is happening right now. Investment is finally happening, but at the same time, a lot of these technologies are in their early stage of life, and a lot needs to be done. And planning, which you mentioned, and having that global momentum behind this is the key to make sure that we move towards this direction.
We have another raised hand from Lee. Lee, would you like to take the floor?
Yes, Sadia, thank you.
Thanks.
So I work with the Energy and Petroleum Regulatory Authority. And recently we launched our Energy and Petroleum Statistics publication, 2021. One of the things we are considering going forward is including a section on CO2 emissions as part of regulatory outcomes.
Yeah.
You mentioned there are different methodologies for greenhouse gas emission computation. The one from IEA, UNFCCC, and also from studies, the other grid emission factors, which we've also managed to establish. Now, my question is there a recommended methodology for this CO2 emission computation, which we can consider adopting? And also, are there references for, say, fuel-specific emission factors, which we can use? Thank you.
Yes, thank you, Lee. This is great that you see that such efforts are happening within your organization as well, which I'm happy to hear. So in terms of the methodology to use for estimating emissions, the most important known one are the 2006 IPCC methodology for greenhouse gas inventories, which is what's used for our estimates. And at the same time, countries also base their submissions to UNFCCC based on that guideline. So that's the global guideline, which provides the basis for estimating emissions. Within the guideline, there are various different methods which can be used based on the level of available data. For example, as mentioned, we use the simple method of tier 1, which we use default emission factors per fuel for estimating the emissions. But on your side, you might have country-specific emission factors available. In that case, then you might be able to use the tier 2 methodology within the guidelines, which could even have more accurate results than our estimates. Or you might even be able to go further and do a modeling and facility-specific measurements. So it all depends on the level of availability of the detailed data, as well as resources available to be able to base the estimates are. But all this is again based on the IPCC guidelines, which provides the harmonized international methodology for such estimates. I think, yeah, let me know if that answers your question. I hope it does. Thanks again, and I'm happy to hear that such efforts are happening.
Thank you. We have another question in the Q&A box from Dennis. It is said that nuclear power is not fossil fuel, it has little emissions, more so from power plant construction machines. Is it true to say that this power source, so nuclear, will be much preferred for clean and huge one-stop power generation compared to other little capacities options, including solar, wind, and hydro?
Yes, thank you. As you have correctly mentioned, nuclear is a non-emitting generation source. So similar to renewables, it's considered a low carbon energy source, and it does not nuclear generation, besides obviously any energy used to construct the plant. But the actual generation itself does not correspond to any greenhouse gas emissions. So it's a low carbon generation source. And as you also have correctly mentioned, the nuclear energy does not have the problem of intermittency, which comes with the renewable sources, which we sometimes have the sun shining and the wind blowing, but not all the time. So nuclear, it's one of the pieces of the puzzle that we need. And it has been also helping across some countries, providing the base power on the grid. So it is part of the solution, and depending on the natural circumstances, as you know, there's also geopolitics involved in that, and it might not be easy to implement it everywhere in the world. And at the same time, it's a very expensive technology to build. So it is part of the solution, and especially with the new generation of reactors coming, the small modular reactors, it could be even easier to have more granular, smaller size plants instead of the typical traditional massive power plants. And that might also increase the chances of more countries to be able to add that to their electricity generation mix.
Thanks, Puya. I don't see any other question. One more. Would one say that nuclear plus sub-Saharan Africa is equal to disaster? Mostly due to the challenges attendant with the waste management, particularly in the light of poor solid waste management practices. So do you think nuclear and sub-Saharan Africa, it's compatible?
I mean, I'm not an expert within the Saharan Africa environment. I think that anywhere, if proper management and procedures are put into place, it can be dealt with properly. And I don't want to exclude anywhere in the world, including sub-Saharan Africa, from having the opportunity to have proper nuclear generation. But as you mentioned, yes, one of the issues with nuclear generation is waste management. And again, there has been a lot of progress in there in terms of how to deal with the waste and ensure that they're stored properly without contaminating our natural resources or proposing any risks for our lives.
Thanks, Puya. Any more questions? I think since we started the training, it's one of the sessions where we got the most questions. So that's very nice. And thanks, Puya, for taking over all these questions. If I don't see any more questions, don't hesitate. Today we have some time, so we can afford to take more questions. We just have the exercise to correct. No. Well, then if we don't have any more questions, we'll move on to the next, to the exercise session. And I want to thank again, Puya, very much for sharing your knowledge with us, answering the questions, and also commenting on the different topics. It was very interesting.
Thank you, Zakia, for having me, and thanks everyone for the very interesting, engaging conversation. And I hope you enjoy the rest of the session. Bye-bye.
Bye, Puya. So now I will share the exercise sheet. Okay. So I don't know if many of you got the opportunity to work on this exercise on balances and emissions. And I want to thank the two participants who sent me questions by email. I received another one this morning that I will reply later today. So yeah, don't hesitate to try to do the exercise, send me your questions. I know that sometimes it's when you do the exercise that especially the conversion from one unit to another can be a bit tricky. But I'm very happy to receive by email your answer sheets and to discuss with you. So this exercise, it's a continuity of the first one. So if you remember last week, we looked at the commodity statistics for natural gas. So we had the data in million cubic meters. We were provided with the calorific values, which was in gross terms. Then we had to convert the data in terajoules. So taking the data in million cubic meters and using the appropriate calorific values to get to the energy terms. Then we had some data for electricity in gigawatt hour, and we had to calculate some efficiency. So that was last week. And this week, so today we are asked to use that information to build the energy balance for the country. So as we said, the energy balance, you have all the different products, but in the same unit. So here we want to calculate the energy balance in terajoules net calorific value. So energy balances, it's always in net terms because we are interested in the useful energy. So now we have these yellow cells that were empty, and we are asked to fill out some of them. So the first question is, why coal and electricity plants? So C11, so why is this number here? And as well as crude oil refinery, so this number, so E12, negative. So why do we have in this block here some negative numbers and positive numbers? And we have this number here, F12, which is positive. So, and also K11, which is positive. So again, here we go back to the concept of the energy balance. So in the energy balance, you have the transformation block where you have inputs and output of different products that goes into different processes. So for the refinery, you have your input of crude oil to produce oil products, or and also you have, for example, for electricity plants, you have some products that is used to produce electricity. So this makes you have a sign convention. So in the energy balance, inputs you have a negative sign and outputs have a positive sign. So here for coal that is used in electricity plants, this is an input, so you put a negative sign. Crude oil that is used in refinery to produce oil products, so your crude oil has a negative sign, and your oil product, which is the output, has a positive sign. Your amount of electricity produced from the different oil fuels, so you have coal, natural gas, hydro, wind, PV that is used to produce electricity. So these inputs are negative and your electricity output is positive. So the second question is, using the results from the first exercise, complete the simplified balance for 2019. Use terajoule as units. So you need to fill out for natural gas here, and as well as hydro, wind, and electricity. So here, for natural gas, here, if we go back to this exercise, I'm sorry, we had already calculated in terajoule last week. But here it's in terajoule gross calorific value. And our energy balance, it's in net calorific value. So if you remember from the presentation, we said that the difference between your gross and your net calorific value for natural gas, it's 10%. But for coal and oil, it's 5%. So here to convert it into net, you just take your production here from the first exercise, you multiply it by 0.9 to get your net calorific value. So you do the same for the different flows. You just link it to the other exercise times 0.9. And you also do it for electricity generation. So here we already had electricity generation in gigawatt hours. So here it's just equal. So for coal, it's 688, because here, you know, coal 688. You do the same for the different products, and your total, it's the sum here of the different electricity production by fuel. So you know that for hydro, you had 120, 11 for solar PV, and 10 for wind. So here, we already said that for hydro, solar PV, wind, there's a 100% efficiency based on the IEA method. So here we just need to convert from gigawatt hour to terajoule, because here your electricity generation, it's in gigawatt hour, but here your table here, it's in terajoule. So here what do? We multiply by the appropriate conversion factor. And here it's given 1 gigawatt hour, it's 3.6 terajoule. So here, given that it's 100% efficiency, it's a direct conversion. You multiply each fuel by you convert to terajoule. And we also said that here in production, you just remove the negative sign, which we had applied a sign convention in the transformation sector. So it's just equal to this, minus equal to this. So that's done for question 2. Question 3, looking at the refinery transformation, do you see anything wrong? Why? So what do we see? For refinery transformation, you have minus 495 terajoule input for crude oil, and you have 532 terajoule as output. And then in your total here, you have plus 37. So here we see that your output is greater than your input, right? And if we calculate the refinery efficiency, so here I calculated it. So your output divided by your input, you get 107%. So it's above 100%. It's above 100%. And so it's too high. So this is not correct, because energy gains, it's not possible. And it means that either your output, your oil products output, or your crude oil inputs are wrongly reported. And this can be due to several reasons. You could have used wrong calorific values. You could have incomplete observations when collecting data, or maybe you double counted something. But when we look again here at the table, we see that it's most probably due to oil products, because you have this big statistical difference here, 156. So this statistical difference, it's an indication of the quality of your data. So it means that there's something that's wrongly reported here. So that was for question 3. question 4, calculate the CO2 emissions for total supply and electricity generation for each fossil fuel and as a total. So here we have to calculate the emissions for total energy supply. So as we said, and here you're provided with carbon emission factors for coal, natural gas, crude oil, and oil products. This is in ton of CO2 per terajoule. So how do we calculate emissions? You take your amount of total supply for coal, you multiply it by your coal emission factor. And so here it's in terajoule, and your emission factor, it's in ton of CO2 per terajoule, but here you want kiloton of CO2. So to get to kiloton, you have to divide by 1000 as well. So you take your amount of supply times your emission factor, divide by 1000. You do the same for natural gas, your amount of natural gas times the natural gas factor, divide by 1000. And for total emissions, you just sum it you sum the different products. Now for electricity generation emissions, here you would take for coal, how much coal has been used to produce electricity, but given that you had it with a negative sign, when you calculate emissions, you remove that sign. So it's minus your 8,255, multiply by the coal emission factor and divide by 1000. Same for natural gas. There's no crude oil used in electricity, so it's 0, no oil products, and your total, it's the sum. So that's for the emission calculation, quite simple. Then the second question in question 4 was calculate for each fossil fuel generated electricity, the CO2 emissions intensity in gram of CO2 per kilowatt hour of electricity generation. Calculate also the average electricity carbon intensity. So to calculate the electricity CO2 emission intensities, you have to divide the emissions related to the electricity plants by the electricity output. So here for coal, you take your amount of electricity generation emissions for coal, divide by your coal electricity generation. But here we want to get gram of CO2 per kilowatt hour. And here you had gigawatt hours. So here you have to multiply by 1000 to get gram of CO2 per kilowatt hour. You do the same for natural gas. Your natural gas emissions from electricity generation divided by your electricity generation from natural gas times 1000. And for the average, you would take your total electricity generation emissions, divide by your total electricity generation times 1000 to get the correct unit. So that was the end of this small exercise where we tried to look a bit about the different concepts behind the energy balances, but also some simple emissions calculation and indicators that you could derive from the emissions numbers. So I think this is a very good exercise to practice, and I really recommend you to try to do it by yourself. And let me know if you have any questions when you're working on those exercises. I don't see any questions, but yeah, I think for this exercise, the best approach is to try to do it by yourself, given the explanation I just gave you, and send me by email your correction. I can even write down in the chat here my email so that you don't have to look for it. And then we can look together at if there's something that you have not understood. If we don't have any comments or questions, then I think we have reached the end of this session. I hope that you found it interesting and useful to your work, and I mean, at least for me, having worked on energy balances for many years, I found it very interesting. And so we'll meet again next Thursday to look at the final part of the statistics module, where we will look at energy prices, so end user prices, and also energy efficiency indicators. So for energy efficiency indicators, you will see that we go beyond energy balances, where for energy balances, for example, you're just looking at the residential sector energy consumption. But when you look at energy efficiency indicators, you have to go even deeper and look at appliances, and so we really go into more details. And for energy prices, at the IEA, we collect information on end user prices. For example, we collect data for gasoline, diesel, LPG, electricity tariffs, and so you will learn more about all this work and the methodologies behind. So thank you again, everyone, for your attention today for the past 2 hours, and talk to you on Thursday. Bye, everyone.